Okay, so the next set of slides, still in chapter 3, but we'll look at relations. And I have two sets of slides. One is be more general network kind of. The next one will be more on trees, hierarchical information. Okay, so I understand so visualization of graphs, and I will explain what a graph is. Mathematically, it means something different, or it means many things. I know it's a visualization course, but this does not, the graph that I talk about here is not a visual thing. It's a mathematical entity. And it represents relations, a type of binary relation. So we're going to look at different types of graph visualization, um, kind of stretched out circuit board. Then we'll look at diagrams. Basically, the last two, when we move to diagrams, we're going to look at relations that are not binary anymore. Multi, you know, T relations that have more than two elements in it. So here is what a graph is. And I will try to be consistent maybe during the course and not use graph for something else, but it's possible. Because graphs comes short for graphics. But in this case, it has nothing to do with graph. I don't think it does, the original mathematical definition. You would probably know it as a network. That's one example. Typically represented like this. But in mathematics, in discrete math, actually, graphs are pretty much a big chunk of discrete math is concerned with graphs. So what a graph is, it's a graph G is going to be a tuple, two things, a set of vertices and a set of edges. Okay, so the vertices in this figure that I have here, in this picture, are 1, 2, 3, 4, and 5. So V is really a set that has 1, 2, 3, 5 in it. The edges are basically the links between those nodes there. So there is an edge between 1 and 2, and that's why I call these relations binary, because an edge always has two things. So it has one vertex that is linked to another vertex. That's by definition. So that's why it's binary. So it's a phone call. I call somebody. It's not a group meeting. It's not like we talk 3 or 4 people getting together. Then we go into relationships that are not binary anymore. Have more than 2 members inside of them. So they get more complex. And that's kind of towards the end of this set of slides that we cover them. But the big chunk of this set of slides is going to be on graphs, on these mathematical entities. So if I were to write E is always going to be a set of these edges, 1 and 2, 2 and 3. So it's just a set, a bag of those edges or links. So they're very popular. They can represent a lot of data nowadays, relationships between two things when they get connected somehow. A graph can be, and that's how you interpret the E. It can be directed or undirected. So the figure that I have there doesn't show any direction, so that is kind of an undirected graph right there. But if it were direction, then you can say that the first item that you put here is the source of the edge, and then the second item would be the destination, so from and to. So again, two people being together in the car, that's an undirected relationship. But if I make a phone call to somebody else, I am the source, the other person is the destination. So it becomes directed. So these are kind of two big chunks of graphs. For the homework, it's going to be an undirected graph. Please keep that in mind. There is no direction in there. So I think that's the first thing I say in the homework. The other thing about these graphs, how do I represent them mathematically? And actually, there's a lot of algorithms in computer science that can work really well on one or the other of the representations. So these are memory representations, not a database. I'll go to a database in a second. So one way to represent a graph would be as an adjacency matrix, and that's how I kind of do it in the homework. So what you can see, really at the top, you can see the vertices, but they're repeated on rows and columns. And then an edge is represented by something that's not 0, in this case a 1. So that tells me there is an edge between 1 and 2. This being an undirected graph, there's also an edge between 2 and 1. So the graph I have in the unless if I messed up that one, it should be symmetrical. So if you look at this diagonal here, the graph is symmetrical on that diagonal. So if 1 and 2 are connected, then 2 and 1 must be connected. There's nothing, I mean, being a matrix, again, you kind of have to have both of them. And again, there's algorithms for that. The other thing that may happen here, this representation is powerful enough to even represent something like distances. The distance from here, there's an interstate from here to Memphis, and that's 120. So instead of just putting a 1, I can put 120 between Little Rock and Memphis and kind of have it in there, have the distance put in there. If it's 0, that normally means there's no link. We're not connected. So that's kind of some things you can do with this matrix. That's why it's so popular. It's very powerful. You can even have a node, but notice that in the mathematical definition, there is no idea of a distance. That's kind of something you have to add on top of it. But also there is no requirement. I can have an edge that goes from 1 to 1. There's nothing preventing me from doing that. But for the most part, if in a simpler graph where you don't allow one node to be connected to itself, that diagonal would be 0. And there's so that's kind of what the adjacency matrix comes in. So when you look at the homework, this is what I tried to present. I gave you the name of those vertices. It's 1 through 10. 1, 2, 3, 4, 5, 7, 8, 9, 10. Don't try and come up. I mean, you could. It's not going to hurt it that much, but don't try and come up with something. That's the names that I've given you. It's an undirected graph, and it has no distance built in. It just edges. So it's the very, very straight, plain vanilla graph, the simplest you can get. Another way to represent it, so this is really easy for a computer or a lot of programming languages. They can process matrices easily. It's just easy for an algorithm. Some other algorithms kind of prefer an adjacency list, but this structure is a little bit harder to implement computationally in memory. Why? Because for 1, for example, the list is 1. It's only connected to node number 2, but 2 is connected to 3 of them. So you kind of have variation. Some of these are longer than others. You have to actually have some sort of a list structure to do that. So that's another way to do it algorithmically. And let me erase this. Finally, if I were to build a database, if I want to do it in a database, remember, database needs to be like a table. So that's not, it looks like a table, but the problem with it is that if I add one more node, then I need to add one more column. And I don't want to do that to a database continuously, adding more columns for nodes. So the best way to put it in a database is really, if you want, edge 1 and edge 2 for an undirected graph, or a from 2 for a directed graph. And then this graph here will be 1 and 2 are connected. Then I can say 2 and 3 are connected. I can say 4 and 3 are connected. 2 and 4 are connected. And so forth. So if I want to add a 6th node here, that's connected to 4, all I have to do is add a 6 and a 4. So that kind of, it works better in a database to have it that way. Some of the programs that you can do, GIFI comes to mind, recognize that type. So they recognize that structure, and they kind of scan through it to figure out look at all numbers or text that you put in there, and they figure out these are the vertices, and then they can figure out, obviously, the edges are, each edge is one entry in that database. So that's kind of the database way of representing graphs. The previous one that I showed you, it's one big structure of representing graphs, and I'm a little bit biased here. I have not seen many good representations, but of that, they tend to look like a hairball for any normal size graph. It's a node link diagram. So vertices are nodes, and edges are going to be links between those nodes. It almost looks like a molecule stick and ball diagram if you were to build a molecule from the old chemistry world. So why don't I think you have to have a pretty nice algorithm, and I know they have at least one, or they used to have, I haven't followed graph drawing community in a while, but they used to have 2 big conferences every year. They came up with new ways of drawing these graphs. But look at the big difference here. You don't understand anything what's going on from that representation. It's the same graph, but if you start pulling it apart, this one is a much better representation. But how do I know to do that? That would be the problem. And to kind of understand how big of a problem it is, that's the purpose of this homework that I'm giving you. It's only 10 nodes and not that many links. There's a lot of zeros in that matrix that I put out there for the homework. But you'll see it's not easy to build. So just to give you an idea, and there's many ways to do it. And also for the homework, I'd like you to have a node link diagram. Don't do anything more creative than that. So not a lot of creativity, but you're going to have to figure out where to place the nodes to make the network kind of visible. So that is, to me, that is the biggest problem with the node link diagrams, is where do you place the nodes in order to understand anything out of that. If you have a good placement, then the graph is kind of self-explanatory. If you don't have a good placement, it looks like a hairball. It's very, very tough to do. Also, notice that part of the graph does not have to all be connected. The 3 components, so there's a connected components if you want. So that graph is really split into 3 parts, and if you were to travel, you won't be able to follow the edges to kind of travel from node B to node A. There is no connection between them. From A, you can only go to H and F, and that's it. So those are kind of disconnected somehow, and it's possible for graphs to be like that. There is nothing in there. That's actually part of why is this visualization good? It's because it pulled them up and it shows them. The one on the C is better than B because it pulls them up. Here's an example of a node link diagram that's more intricate in that here I have a subgraph that's represented inside. Here I have another subgraph, and they're also linked together, so it can get as crazy as you want. Some of these are pictures. I have labels. Some of them use color also, so I kind of start to use whatever I can from representation to put more information about each of the nodes and each of the links in there. Here's another one. Again, it still looks like a hairball. I'm not sure if it's a better way to do it, but they at least group them by, this shows, I think, kindergarten, 4th grade students. So girls are on this side, boys are on the other. You can see there's only one connection between the 2 groups. It does show that particular connection, but maybe it could have done it better. But if you start moving nodes around, then you're not going to be able to see the fact that boys tend to stay with boys, girls tend to stay with girls. Another one, social network. Again, to me, I have it here mostly because why did they decide to give it this shape? I don't know. It also shows that you can color the nodes by age here, and you can see that people kind of tend to stay within their age. young, old, or middle age and old when they talk to each other. So for a graph, if I want to do a node link diagram, what do I need to do? I need to figure out for the nodes their position in space. Sometimes the position may be fixed, and I have some examples coming up. But if the position, the ones that I showed you so far, the position was not fixed. You can place them anywhere. So I need to figure out their position, their retinal properties. If you want their marks, what shape am I going to use? I'm going to use pictures. Are going to be 3D, 2D. They're going to have colors. So everything can be, I can make it as complex as I want to. And the label, sometimes it's present there. For the links, I need to determine their path. So there's nothing saying that the link needs to go straight. I might be able to do another link that goes this way. So I need to figure out their path. I need to figure out their properties. Do they have, how big they are? There was a presentation today that had these links between taxonomies. Some of them were wider than others. So there's stuff I need to figure out. And their path was interesting. It wasn't straight. They kind of used a double curve there. What color, what label am I going to label them, and so forth. So there's quite a lot of work to do in graph drawing. Like I said, you can probably take a whole course on it. I'm just barely touching it. And also, if you read through the book, they're going even faster than I go. I go into more detail. Also, this has implications. Taking that course in graph drawing, I kind of, well, you can distill it in maybe 3 main things. It's almost like Tufte principles, 3 main principles that may end up creating graphs that are clear, relatively clear. So principle number 1, reduce intersection of links. Why? Because it becomes like a hairball. If I try to reduce intersection and kind of get as few intersections as possible, then it makes it easy to, so here is one representation I have. If I can have it like that, there's a lot of intersection there. What if I put another node here and another node, and let's draw it straight through them. The same graph, if I do it right, I might be able to just do one node linked to this one. So it was this one here, linked to this one here, and that's linked to this one. So I put it in a line, and then the last 2 are going to be like this, so I have no intersection. It is clearer than what I drew at the top. Okay, so intersections make it hard to figure out what's connected to what, because you're going to have links on top of links, and links on top of nodes, and nodes on top of links, and it's a mess. So you really want to declutter that, get rid as much as you can. It's not always possible to reduce intersections. If there are too many of these edges, you won't be able to do it. Actually, the name for it, it's called, if a graph can be drawn without any intersection, that's called a planar graph. You can put it in a plane, mathematical plane, not airplane. For example, maps. If I take a map of the United States, Arkansas is neighbor Texas. It's already on a map, so it's obviously planar, because I don't have a state that goes on top of another state. So maps, by definition, are planar if I start put them in a graph with the neighbors. But not everything is possible to do it that way. So, but at least I try to reduce the number of intersections. If it's not a planar graph, how can I reduce it? The next principle, if you want, or goal, is to reduce the variation of lengths. Here is what happens. If I have one node and all the links are the same size, kind of what I can do is look around this circle here, and all its neighbors are going to be in that area. It just makes it easy to determine neighborhoods. If I have a lot of variation, for example, this node is also linked to a node right here, it's going to be really hard to determine a cluster has no meaning. The fact that you're close to a node means nothing because these links can be arbitrarily long. So if I'm able to have a graph where the links have about the same length, then it's going to be easier to estimate. Things that are close together are really close together mathematically, logically. And things that are far apart are really far apart. There are steps in between to get there. So that's what this idea of reducing the variation of length. Again, for the homework, I don't necessarily want you to, it's a visual thing. I'm not expecting you to measure the number of pixels required for that link. But if visually it looks like they're about the same, then give the credit that it's about the same. Now, if it's clearly one is longer and the other is shorter, then I'm kind of violating that goal. I'm not able to do it. And the final one is to reduce the bending on the links, make the links straight. Again, if they're straight, then neighborhood has a meaning. A cluster means a cluster, and it's easier to follow. So rather than have a link that kind of goes all around and connects here, have it straight. So many times having a straight link actually has a benefit. Or sometimes they're slightly curved, but I don't know. If they're all curved exactly the same way, then it's easy to follow. But if the curving varies, then it's just going to be hard. So these are the three goals. If you're able to maximize all of these, then you should have a graph that's easier to understand than when these are violated. So in terms of layout, I was telling you sometimes there's nothing I can do about the position of the nodes. They're already there. If I try to draw a graph of streets in the United States, or if I have them on the map already, I have the cities, then I'm not going to move cities around. I'm not going to take Chicago from the north and put it in the south, because that doesn't serve anyone's purpose. So sometimes I'm stuck with the position of the nodes. And sometimes, I can maybe just vary the links. And I have two examples, one pretty famous. And this is London Underground. It's a famous map. I think the real map looks like this. Looks like a spaghetti thingy. There's a lot of bending. This is the actual route that line follows, or the red line. You can kind of see it. But what people realize, if you're underground, the fact that you're turning a little bit, it makes absolutely no difference to you. So it's the first example. What did they do? First thing they did, they straightened all the links. Now, if you're on a street, you may want to know, if you get closer to you're not going to be able to get off at this in between stations anyway. So it makes no difference the fact that you are curving a little bit. So if you look at the actual metro, which is pretty popular nowadays everywhere, all of these are pretty straight. They only kind of go at 45-degree angles. Other than that, they don't show you all that spaghetti thing. So it's easier to remember. Things are straighter. So that's one goal they did here, is they reduced the bending of the links. They eliminated that, and it makes it easier to remember kind of where you are. Having the exact map doesn't matter. I mean, even if you look at the river of Thames, it's also straightened. All you need to know which side of the river you're going to be when you cross it, and so forth. The thing they've done, actually, did they reduce intersection? No, they actually want to show intersection. In this case, you want to show where you can get off and move to the next line. So get off the red line and go to the green line that is there. So you want to show intersection. That's not an issue for this one. But they also did something else. If you look, it's obvious even in the city center, but it's more obvious. I think I can even explain it better if you look at it edges. Do you think those stops are exactly the same distance? No, wherever the population is. No, they kind of go to where the center is. They're not going to stop it in the middle of nowhere just because. But if you look at the representation on the map, they tend to be pretty, at least for one line, they're equally spaced. All that tells you, it allows you to kind of count how many stations. I need to go 3 more stops, I need to go 4 more stops. That's all I need to know. The actual distance is not going to help you as a traveler. May help, yes, some of them may take longer. One may take 2 minutes, especially in downtown, from one stop to the next. You go to the periphery, it may take 10 minutes between, but that's not represented here. You're not going to get that information. All you're getting is the number of stops that you need and where you can get off. So they did reduce the variation of link length. So the variation meaning that the edges connecting the stations tend to be about the same size. And they made everything straighter. And they even aligned the angles to reduce bendings there. It doesn't look anything like this. It's easier to remember. The second part here, it's kind of an article they've done, but it's just, again, a lot of these things are showing where can you be creative with these. And here is what happens. This is a view of the US landline network a long time ago. And there was an earthquake on the West Coast. Now, everybody, you're probably familiar with your Wi-Fi's and Ethernet and all that. They have a different way of sending packets out. So if you talk on Wi-Fi or normal Ethernet, normal Ethernet, I think transport protocol, whatever that is. My networking is rusty. But what happens there when you talk, your packets almost follow the same. Basically, your voice gets chunked into packets, and one packet is sent at a time, received at the other end, and put back together. And the person, it appears as if you're talking coherently. But really, what you're sending is a bunch of packets on the network. That part is true for landlines as well as for our Ethernet-based kind of internet connectivity. On the internet, however, there's no issue. It works almost like mail. So if you send something if you send 2 packets from here to the same address in New York, they may not go the same route. The first packet may go from here to Memphis. The second one may go up to Chicago next. So eventually they get there. Well, that's kind of the normal way the internet works. So but a normal phone landline network, when it connects, what it needs to do, it reserves a route for that call. That's why the quality is a lot better on a landline than, that's part of it. And you don't get the lag. When you talk on a landline, it's very smooth. You don't stop and if you do a video chat with somebody, sometimes it stops and their voice gets faster or that doesn't happen on a landline because they do a completely different type of networking where they reserve the whole circuit. So really, each point on the route reserves space for you to talk. The problem is when the problem is that you can get into roadblocks. If I reserve the room, if I'm trying to go from here to California and I need to go through 3 substations, and I'm only able to reserve room on the first 2, but the third one is full, it won't allow me to reserve room. What happens is I already reserved room on the first 2. And then I can have it's almost like a roadblock, like a gridlock traffic. I'm waiting on them to finish because they reserve room, but they're waiting on me to finish because I reserved only partially. They have partial reservation, I have partial reservation, but neither of us can go any further. Again, it's exactly the same concept as gridlock on a street or a city street. Everybody's turning on everybody else, is waiting on them. So that's what may happen. That's a danger on a landline. And part of it, they're really afraid of that. And that's what they want trying to visualize here. Do we have any stations where a gridlock can occur? What they do really, they kind of do an approximation and they say, we're never going to have a station that goes beyond the 90 or, I don't know, they put a number there. So all our stations, substations, are never going to be reserved more than 90%. Once we hit that capacity, we start destroying circuits and kind of retry it again. Because otherwise nothing goes through. And again, this was in the, I think the earthquake was 70s or 80s, so it was a long time ago, and the network, that was the only way of communicating with people over there. You had no other way, no cell phone, no internet. So that's what they're trying to do. So anyway, the telephone network, you have the substations. They're going to be, there's some white circles there. It's a complete hairball. You cannot even see the United States on the links. And then for each link, what they have is the amount of calls going one direction, the amount of calls going the other direction. Okay, so this is a directed graph at this point. So it gets even harder to represent. That's why it's so busy. So they figured out, what if we use thickness? Obviously, we cannot put all the labels for all possible calls. You can see there's a lot of them right here. So no labels, but what if we use thickness? So that would be an undirected graph. We use thickness, which again was one of the presentations today was using that. And if it's a directed graph, then you can use two links, but again, you're making things worse. So their idea was, okay, what if we use half, we split the link in half, and the first half shows the traffic going this way, the second half shows traffic going this way. Still, and that's what you're actually seeing. Not very clear. Okay, so they kind of went one step ahead. How can we make this even clearer? They went ahead and, let me delete everything. Here's how they're going to make it clearer. They're going to cut the middle. They're only going to show the beginning and the end for these links. And that's it. That's all you're going to see. So here is, again, here's the one where it shows the entire link. Here's the one where they cut them. And it starts to get a little bit clearer, the map itself. You kind of see where the substations are, which way traffic is going. And I think it's pretty obviously that on most of the country, they go this way. From the substation, it kind of goes this way. On the East Coast, they tend to go the opposite way. People are trying to call back to the rest of the country. Now, what you're losing, for example, look at this yellow area there. This yellow, there's two links. You can see them in the big map. You can see the connectivity, where they're going. On this, once you start cutting, there's a drawback. Here, it's even hard to see. There are two of them, but it's even harder to see where they're going, where they're going to end up going. You kind of have to guesstimate. So yes, I can clean up the map a little bit and see more, but I won't be able to tell which node I'm really hitting. Am I hitting this substation that's red, or am I hitting this substation that's blue right there? So the red one is already at capacity. It's out of, they're not going to accept any more calls, and they're going to make anything else. So that's kind of the drawback. Once you cut the middle, it's going to be really hard to figure out where this you're going to have more than two or three, or one of them may be even further away. So it's just going to be a little bit, where does it actually stop? That is the drawback with this. And I think we're out of time.